Hello and welcome. In this Ansys how-to video, we will discuss the details of the proximity size control in the local sizing task of the Ansys Fluent Meshing Watertight Geometry Workflow. So let's get started. The local sizing task allows us to gain better control over the sizing of the mesh elements by letting us define mesh size controls that operate on a specific localized portion of the domain. Proximity size control type is used for refining the mesh by specifying the number of cells to be used to resolve gaps either between edges or faces. Let's learn about this size control in detail by getting our hands dirty with Watertight Geometry Workflow in Ansys Fluent Meshing. Let's start Fluent in meshing mode, set the number of processes and the working directory accordingly. Once Fluent launches, select Watertight Workflow from the drop-down menu and import the provided geometry as shown here. This geometry consists of an enclosure around a PCB containing geometrically identical pairs of heat sinks and capacitors as shown here. Keep in mind that this is a representative geometry intended for instructional use only. Select Yes for this question. Now under Size Control Type, select Proximity. You will notice that additional settings are added to the task. The proximity sizing requires 4 main parameters to be defined: minimum and maximum sizes, growth rate, and the cells per gap. The local min and max sizes allows us to specify the minimum and maximum sizes of the elements for the surface mesh respectively. Keep in mind that these sizes are measured between the proximity boundaries. The growth rate specifies the increase in element edge length with each succeeding layer. These settings prevent the mesh from becoming too fine or too coarse on the scoped surfaces. Now let's select walls underscore heatsink 1 and set the local min and max sizes to 0.3 and 1 respectively, and keep the default value for growth rate. The main parameter for this control type is the cells per gap setting. This setting allows us to set a minimum number of layers of elements to be generated in the gaps. These gaps are defined in either of two ways: the area between two opposing boundary edges of a face or the internal volumetric region between two faces. Set the cells per gap to 4. Lastly, we need to define the scope of this localized size control in the scope to field. We can localize the size control to faces, edges, or face and edges. The last option, that is faces and edges on proximity, can be used when the prescribed number of cells across the gap need to be respected on all transverse sections of proximity walls. Let's set the scope to faces and click on Add Local Sizing. You can see that the proximity local sizing task is added to the workflow. Now let's create a similar local sizing for walls underscore heatsink 2 but set the cells per gap to 2 to see the impact of this parameter. We will keep the defaults for the generate the surface mesh task as we want to focus on the local sizing in this video. Click on Generate the Surface Mesh and Fluent Meshing will create the surface mesh based on these settings. Let's look at the generated surface mesh to see the effect of the proximity local sizing. First, let's hide the enclosure, the inlet and the outlet surface, and zoom into the heat sinks. The impact of the proximity size control, specifically the cells per gap parameter, is clear when looking at the mesh for the two heat sinks. The surface mesh for the heatsink on the left has been generated with cells per gap of 2, whereas the one on the right is generated using a cell per gap of 4, which is evident from the number of cells that are present in the gaps. Before we wrap up, let's quickly see the effect of different scoping options. Let's go back to the proximity size control for heatsink 1. And change the cells per gap to 2 and select edges under scope 2. Now let's generate the surface mesh again. Here is the generated surface mesh. You can clearly see the effect of scoping the local sizing to edges compared to faces by comparing the surface meshes on the two heatsinks. The local sizing is applied only at the edge of the face, where the size of the element increases, while moving away from the edge where the sizing is being applied. So to summarize, in this video, we looked at the proximity size control for the local sizing task. This size control allows us to control the local sizing based on the number of cells per gap setting, which we understood using a hands-on example. And with that, we have come to the end of this video.